Hey guys, so today we're going to be continuing on our chapter about solutions by specifically talking about how ionic substances react in solutions, as well as how some non-ionic substances act like ions when in solution. So in this lesson on ionic solutions, we're going to be going over how to identify and write dissociation reactions, also identify and write ionization reactions, and then use those two different types of reactions to calculate the concentration of ions in solution. So just a reminder, ionic compounds are always made of a positive and a negative ion, which then bond to one another to form a crystal lattice structure. Ionic compounds are electrically conductive because of their ions, and they are also soluble in polar substances like water, because the dipoles of the water, that's slightly negative oxygen and slightly positive hydrogen, will attract to the oppositely charged ions and pull the ions apart from one another. When ionic compounds dissolve in water, they separate or dissociate into the individual ions already present in the compound. So that is what a dissociation reaction is. It's just the pulling apart of ionic compounds into the two separate ions. With a dissociation reaction, you're always going to have the solid solute on the reactant side and then the individual ions on the product side. You would then write in brackets AQ to show that it's in solution or aqueous. Though to be completely honest, and on like tests and quizzes and stuff, I don't care if you write in the like S for solid and the AQ for aqueous or G's for gases or anything like that. But technically that is how it should be represented. Water is not included in the dissociation reaction since the water doesn't actually react with anything. The water molecule doesn't change from a water molecule. It's just the environment that the dissociation reaction has to occur in. So here's some examples at the bottom. So NaCl, which is sodium and chlorine, because we have a metal and a non-metal, this is an ionic compound, and we can just separate that ionic compound into the two ions. Same with potassium oxide. Potassium's a metal, oxygen's a non-metal, so that is an ionic compound. It dissociates by just splitting into a potassium ion and an oxygen ion. In order to figure out what the ion charges are, you can either look on your periodic table, or if it is a compound that involves like one of your multivalent metals, you will have to do reverse crossing over to figure out what those charges would be. So in this case, if I were to do reverse crossing over for potassium oxide here, the 2 becomes the -2 charge, and we don't bother writing in our 1s, so it's just a plus for our metal. Metals are always positive, non-metals are always negative. So I would like you guys to try these 4 examples and then come back for the answer. Okay, so these are what your 4 answers should be. For the first one, we have calcium carbonate. Calcium, because of where it is on the periodic table, always has a charge of +2. And then carbonate is not something you would just know the charge of, but because calcium has a charge of +2, that would cross over and leave a 2 outside of the carbonate, and it hasn't. There's no like little 2 here. So something must have canceled out that 2 and left nothing behind, which means it was another 2. So in that case, you would need to do some reverse crossing over to figure out that the charge of your carbonate is -2. Okay. Next up, we have aluminum nitride. When we break that apart into aluminum and nitrogen, we can just look on the periodic table to figure out that aluminum has a charge of +3 and nitrogen has a charge of -3. Next up, it gave us the name potassium sulfide. So just to figure out what this molecule would look like, I would have to write out my potassium. It has a charge of +1. Sulfur has a charge of -2. And then I cross the charges to get K2S. And then when I break them apart again, I know that my K is just +1 or just a positive, and my sulfur is -2. this is the first case where I had to balance my ions. So because I had 2 potassium on the left-hand side, I also needed to have 2 potassium on the right-hand side. So I had to put a 2 in order to have that balance. And then the last one is probably the trickiest. We have lead oxide here. And so in order to figure out what the charge of lead is, because it is multivalent, we have to do some reverse crossing over. So PbO2, we don't know the charge of lead, but we do know that oxygen has a charge of -2, just because of where it is on the periodic table. So that would cross over and leave a 2 behind the lead. But obviously there is no 2 there, so something must have canceled that out and left nothing behind. The only thing that could cancel out a 2 and leave nothing behind would be something that's worth 2 points of its own. And then on the other side, we have to say, okay, what could cancel out this 2 and leave a 2 here? And the only thing that could do that would be a 4. So if I had a +4 here, that would leave me with a 2 here. That would be a 2. And then I would divide both of those by 2, which leaves nothing behind the lead, and it leaves a 2 behind my oxygen. Okay, so that's how I know that my lead has a charge of +4. Okay, so just to explain that kind of one more time, because I know we'll get confused with this. This is what I started with. I know that I have a 2 crossing over behind my lead. I need to see, how do I get rid of this 2? And it would be to divide it by 2, because that would cancel it out and get rid of it. And then I say, okay, something must have been on this other side, and when I divided it by 2, it left me with a 2. And so of course that must be a 4 that was divided by 2 and left me with a 2. And so the 4 must have come from the lead. Okay, so that's how I figure out what the charge of lead is. And then again, because I have 2 oxygen on the left-hand side, I need to put a 2 in front of that oxygen in order to make it balanced. Now you might be saying, isn't oxygen and nitrogen Hofbrinkel molecules, which means they're diatomic and should have a little 2 behind them? And that's a very good point. The thing is, and it is important to note, that our Hofbrinkel molecules do not apply to ions. Do not apply to ions. What that means is, as soon as something has a charge and is therefore an ion, we don't just automatically put the little 2 there. Okay, we only use that diatomic 2 for diatomic molecules, and molecules are not ions. So when something is an ion, that Hofbrinkel rule does not apply. Okay, ionization is very similar to these dissociation reactions. The only difference is that in the case of an ionization reaction, you are taking a molecule and turning it into ions, but it's not an ionic molecule. You're taking either a weak base or an acid, reacting it with water, and making ions that way. So yes, strong acids will ionize, weak acids will ionize partially. We'll talk more about that when we get into our acid-base stuff. Weak bases will ionize. Strong bases tend to dissociate, and that's because they are ionic compounds. When acids ionize, they always produce a hydronium ion, H3O+, plus another ion. When bases ionize, they always produce a hydroxide ion, which is this OH- ion. And in this case, water is actually involved in the reaction, so it does have to be shown in the equation. So this is what an ionization reaction would look like. This first example here is an acid. We can recognize an acid because it always has an H in the front. We react it with water. Acids always make hydronium ions, which are H3O pluses. And then to figure out what the other ion is, we just look at our acid and we take away the H. And whatever's left becomes our other ion. NH3 is ammonia. It is the only weak base that you need to memorize. So you do have to know that NH3 is ammonia, and you have to know that it's a weak base. But bases like this react with water. They always produce a hydroxide ion, which is this OH minus. And then to figure out what the other ion is, we just take our base and we add an H and a plus. Okay, so NH3 became NH4 plus. So based on that, see if you can figure out what these next three are going to be and then come back for the answer. Okay, so these are the three answers that you should have gotten. So first we have nitric acid, which is HNO3. We know it's an acid, not only because we were told, but also because it has an H at the front. Acids are always going to ionize, so we react it with water. Acids always make hydronium ions, so H3O plus. And then to figure out what the other ion is, we just take away the H at the beginning. And so in this case, what's left is NO3. And in order to figure out what the charge is, like whether it's -1 or -2 or whatever, you just take whatever is directly behind the H and cross it up. So because there's like nothing here, then that's our invisible 1 that gets crossed up there. If this was a 2, this would become a -2 charge over here. Okay. So like just to kind of show another example, if I had like H2SO4 and I was ionizing it, again, with an ionization reaction, we always react it with water. This is an acid because it starts with an H, so it's going to make a hydronium ion. And then to figure out what the other ion is going to be, I take away the H's, so I'm left with SO4. And to figure out what the charges of those H's are, I just reverse cross over my 2. And with acids, your hydronium ion is always positive, which means your other ion is always negative. Okay, so this next one, acetic acid, works the same way. It starts with an H, so it's an acid. We react it with water. Because it's an acid, it makes hydronium ions. And then to figure out what the other ion is, we just get rid of the H. Because there is no number behind the H, that gives us a charge of -1 or just minus for our other ion. Next up, we have pyridine. In this case, you're told that it's a base. Again, ammonia is the only weak base you have to memorize, so you would have to be told that this is a base. But it is a base and it does not have an OH in it. All of these, carbon, hydrogen, and nitrogen, are all non-metals, which means it has to ionize. It can't dissociate if there's no metals here, if it's not ionic. So it reacts with water. Bases always make OH minus or a hydroxide ion. And then the other ion is just going to be our original base, but we add an H to it. So now we're H6 and we add a plus. Okay, so that's how ionization reactions work. Okay, we can then use both these ionization and dissociation reactions in order to calculate ion concentration. So first, usually you'll have to start by writing out either your ionization or dissociation reaction. Then you need to balance it, which we haven't done in these examples. But once we get into these calculations, we can practice that. And then you set up the coefficients, which is also called the mole ratio, in order to determine the concentration of your ions. So let's go over what some of those examples would look like. Actually, before we do that, I'm just going to do like a little chart kind of summarizing some of the differences between ionizations and dissociations, because you will have to know, just based on the compound you're given, whether you should be writing an ionization or a dissociation reaction and how they're different from each other. Okay, so this chart, and hopefully you can read it, I know my writing is super messy, summarizes the differences between ionizations and dissociations. So dissociation reactions occur in ionic compounds. Ionization reaction occurs in acids and weak or non-ionic bases. With dissociation, water is not a reactant. In ionization, water is a reactant. With dissociation, it makes the ions that are already in the compound. So you're just taking the ionic compound and splitting it apart. With ionization, if it's an acid, you're always going to make H3O+, which is called hydronium, and a negative ion. With bases, you always make OH- or a hydroxide ion and a positive ion. By the way, this negative VE is the sign for the word negative, and a plus and then a VE is the sign for positive. Okay, now that we've done that, let's go on to actually solving this problem. Okay, so for this first question, it says I have 0.39 molar solution of lithium nitride. What is the concentration of ions? So my first step is going to be to write out what lithium nitride looks like, so the formula for that. So lithium has a charge of +1, nitrogen has a charge of -3, and then we cross over our charges to get Li3N. That's what lithium nitride looks like. Then we're going to write the dissociation reaction like this. Again, dissociation reactions don't include water. So I'm just going to break this apart into my lithium and my nitrogen ions. Then I need to balance this. So because I have 3 lithium, I'm going to have to put a 3 in front of my lithium. And at that point, it is now balanced. Just a reminder, even though nitrogen is a Hofbrinkel molecule, that doesn't matter when it's an ion. Okay, so now it's balanced. Our next step, which is step 4 over on the PowerPoint, is to set up a ratio between our lithium nitride, or whatever we're starting off with, and then each ion, one at a time. So between lithium nitride and the lithium ion, that is a 1:3 ratio, because there would be an imaginary 1 in front of the lithium nitride and there's a 3 in front of the lithium. Then I'm going to write the concentration of the lithium nitride, which I was given in the question. It's 0.39. And I'm trying to figure out what the concentration of this ion is. So all I do is cross multiply. X times 1 is X. And then 0.39 times 3 is 1.17. So 1.17 molar is the concentration of my lithium ion. Make sure that you label which ion you're talking about, because we're about to find another concentration, and if you don't have them labeled, you can't get full marks for it. So then our next step is going to be to set up the same type of ratio, but this time between the lithium nitride and our nitrogen ion. This time it is a 1:1 ratio because neither of those have a coefficient in front of them. We're still using our 0.39 molar for our lithium nitride. And so when I cross multiply, X is just 0.39 molar. That is the concentration of my nitrogen ion. Okay, you would need to have both of those answers properly labeled in order to get full marks for this question. Okay, for the second example, it's just going to be like an extra step or two because unlike with the example we just did, we're not given the concentration of our solute to start off with. So we're going to have to start by figuring that out before we can then do the rest of these steps. So let's go through how to do that. Okay, so this one says I've added 23 grams of magnesium nitride to water to make 3.4 liters of solution. Determine the concentration of ions in solution. So step one, write out the formula for magnesium nitride. So magnesium, being in the second column, has a charge of +2. Nitrogen, being in the 15th column, has a charge of -3. And then I cross those over to get Mg3N2. My next step is to figure out what the molar mass of that is going to be. So we look on our periodic table and magnesium has an atomic number of 24.3, sorry, not an atomic number, an atomic mass of 24.3. And we are going to times that by 3 because there are 3 magnesiums. And then I will add that to my nitrogen mass. So nitrogen on the periodic table has an atomic mass of 14. I'll times that by 2 because there are 2 nitrogens. And then I'll just solve for what that is. So 24.3 times 3 is 72.9 plus 14 times 2 is 100.9. Now that I have, so that's my first step. Now that I have what that is, I'm going to figure out what my moles are. So moles equals mass over molar mass. We're told in the question that we have 23 grams, so that's our mass, and we divide it by the 100.9. 23 divided by 100.9 is 0.2279-ish moles. Then I'm going to figure out the concentration using C equals N over V. So N is my moles, 22.79. And we're told that the volume is 3.4 liters. Your V does have to be in liters. So if it was in milliliters or something, you would have to convert that. But for now, I'll just divide. And I get 0.067 molar. That would be my concentration of magnesium nitride. Now that I have that, I can figure out what my dissociation reaction is going to be. So magnesium nitride is going to dissociate into a magnesium and a nitrogen ion, like so. In order to balance this, I need to put a 3 in front of the magnesium because I have 3 magnesiums, and a 2 in front of my nitrogen because I have 2 nitrogens. Now that I have that, I can finally set up my mole ratio. So magnesium nitride to magnesium is a 1 to 3, imaginary 1 to 3. I'm going to plug in my concentration right here underneath the magnesium nitride, since it is the concentration of magnesium nitride. So 0.067, and we're looking for the concentration of our magnesium ion. So X times 1 is X, and 0.067 times 3 is 0.201 molar. That is of my magnesium. Put that in the box so you know that it's an answer. And then my, that was step 5, this is step 6. I'm going to set up my ratio again, this time between magnesium nitride and my nitrogen ion, so it is a 1 to 2 ratio. Plug in my magnesium nitride concentration again, and the X for what I'm solving for, which is the nitrogen ion. X times 1 is X. And 0.067 times 2 is 0.134 molar is my concentration of nitrogen ion. Okay, so these two would be your final answer. You, again, would need to have both of them and have them labeled for full marks. Also, I would highly, highly, highly recommend making sure that you label all of your steps in the order that you've done them, like I've done here, and put a box around your final answer. As we get further into this course, you're going to have questions with more and more and more steps until I think the most steps we have is like 11 in the last unit. And if I can't follow the order of your steps and you have a wrong answer, you don't get any part marks for that. But if I can follow the order of your steps and I can see where you've gone wrong, and I can continue doing the steps in the same order as you using the wrong number that you had from a previous step, then I can give you part marks. So for example, in this problem here, which had quite a few steps, if you had gone wrong right off the bat here, finding your molar mass, everything else would have been wrong. But if you had your steps all nicely labeled like this, and I took your raw number and I plugged it into all of your steps that you did from there on out and used your raw number, and everything else was right, you would get 0.75 out of 1. So it can make a huge difference on tests, especially ones with lots of steps like this. Those part marks make a huge difference. So please label your steps, show your work really clearly. It can make a massive difference to your final mark on like a test or quiz and overall in this course. Okay. I would like you guys to try these 4 practice calculations and then come back for the answers. Okay, so for question number 1, we're given an ionic compound. So this is going to dissociate, so it breaks apart into the 2 different ions. In order to figure out the charge of your metal, you will have to do some reverse crossing over. So IRS2, we would start with the thing we know the charge of, which is sulfur has a charge of -2, which would cross over and leave a 2 there. However, there isn't a 2 there. So something, aka a 2, must have divided that away, which means on the other side, something was divided by 2 and left a 2 behind. That something must have been a 4, which is how we find the charge of our metal is +4. Then I balance this by putting a 2 in front of my S, and then I just set up my mole ratio. So it is a 1-to-1 between my ionic compound and my metal ion, which gives us 1.2 molar as our concentration of the metal ion. It is a 1-to-2 ratio, so a 1-to-2 ratio between my ionic compound and my non-metal ion. So when I cross multiply that, I get 2.4 molar for my non-metal ion. For the second question, this time we were given an acid, sulfuric acid, H2SO4, which means that for our very first step, instead of writing a dissociation reaction, we're writing an ionization reaction, which means it has to react with water. Because it's an acid, it has to make hydronium ions. And then to figure out what the other ion is going to be, we just take away our H's, we're left with SO4. And then we reverse cross over this little 2 here to figure out what the charge of the negative ion is. From there, I'm going to set up my mole ratio between my acid and my hydronium ion. It is a 1-to-2. And when I cross multiply, I get 1.6 molar as my concentration of hydronium ion. Then I'm going to set up my next ratio between my sulfuric acid and my negative ion. That's a 1-to-1, so it is 0.8 molar as my concentration of the negative ion. Okay, for the second one, we have calcium iodide. Again, don't forget to cross over your charges to figure out what calcium iodide looks like. It is Cai2 because calcium has a charge of +2. This is an ionic compound because there's a metal and a nonmetal, which means it's going to break down into that calcium ion and the iodide ion. And then don't forget to balance it. And then this question is a little different because it actually gives us the concentration of one of our ions, the iodine ion, and asks for the concentration of the calcium iodide solution. So this time I'm going to set up my ratio between the calcium iodide and the iodine ion. It is a 1:2 ratio. This time I plug in the concentration for the ion and an X for the concentration of the calcium iodide. When I cross multiply, X times 2 is 2X, and 0.3 times 1 is 0.3. And then to isolate the X, I need to divide by 2. So X equals 0.3 divided by 2, which is 0.15 molar. That is the concentration of my calcium iodide. Okay, so for this last one, this time you're not given a concentration of anything, you're given the mass of aluminum sulfide. So anytime you're given the mass, convert it to moles, and then if you're also given a volume like you are here, you can then convert it into concentration. So we'll start with our aluminum sulfide, which we get by crossing over our charges. Aluminum has a charge of +3. Sulfur has a charge of -2, so we end up with Al2S3. And then our first step is to actually find the molar mass of that. So the atomic mass of aluminum times 2 plus the atomic mass of sulfur times 3 gives us 150.14. Our second step is to find the moles. So moles equals mass over molar mass. The mass we are given, the molar mass you just calculated. And when you divide, you get roughly 0.12 moles. Then I can use C equals N over V, plug in the moles I just calculated, divide by the volume in liters, which we're given, and we get 0.17 moles. That is of the aluminum sulfide. The next thing that I did was write out my dissociation reaction. This is an ionic compound, so it's going to dissociate into the aluminum and the sulfur ions. Then don't forget to balance it. We have 2 aluminum and 3 sulfur, so I need 2 aluminum and 3 sulfur on the other side. Then the final 2 steps, is to set up my mole ratios. So between the aluminum sulfide and aluminum is a 1:2 ratio. And then just cross multiply with our concentration of aluminum sulfide that we calculated, and you'll get 0.34 molar as the concentration of the aluminum ion. And then we'll set up our mole ratio between the aluminum sulfide and sulfur ion, which is a 1:3. Once again, plug in the concentration that we solved for the aluminum sulfide, cross multiply, and you'll get 0.51 molar as your concentration of sulfur ion. So let me know if you had any questions about that. And other than that, that's it for today's lesson.